Hello everyone, thanks for watching my talk. I'm Subhajit Das, PhD student from Georgia Tech, USA. Today I will talk about our paper, QUESTO, Interactive Construction of Objective Functions for Classification Tasks. Over the years, machine learning has impacted almost every aspect of human life, solving complex problems in various domains. Solving for such diverse use cases, the machine learning community has developed many algorithms. Each of these algorithms have one thing in common. They're driven by some form of objective function, which are also called loss functions. For example, in a classification task, an objective function may specify that the model should perform well on a chosen class, or may require a model to get certain data instances correct. Typically, these objective functions are constructed by data scientists or machine learning practitioners by writing code. However, such objective functions are hard for users to specify as they are a specific mathematical formulation of their intents. In addition, there is no interactive graphical user interface that can bypass writing codes to construct these functions. This not only limits the inclusion of end users to specify their goals to a machine learning algorithm, but also inhibits users to quickly prototype and experiment with multiple variants of such functions. In this work, we made construction of objective functions interactive by creating a visual interface. Our technique supports interactive specification of objectives, constraints, and weights to these functions, and then translating the function terms such that a model solver can interpret. Interactively and iteratively, users can add, remove, and adjust objectives and their weights to inspect how the function solves the underlying modeling problem. In QUESTO, we are optimizing to select best models as opposed to optimizing the internal logical processes of a machine learning model that makes QUESTO model agnostic. So using QUESTO's workflow, users can construct an objective function, which is fed to an AutoML model solver. This solver creates n classifiers and utilizes the user-specified objective function to select the best model for the task. Our technique uses an iterative model construction and evaluation workflow. QUESTO empowers users to interactively construct an objective function, which is fed to an AutoML model solver such as HyperOpt. In this pipeline, we pre-specify a set of learning algorithms and a set of hyperparameters for HyperOpt to construct models. Per iteration, HyperOpt consumes the user-specified objective function to construct and rank a set of new classifiers in its model selector module. Each of the classifiers are evaluated and ranked by the model selector based on their performance on the supplied objective function. Finally, HyperOpt reports back top k best classifiers for QUESTO to visualize. Next, I will present QUESTO's user interface that allows construction of classifiers on a tabular data through the specification of interactive objective functions. The major components of the interface includes a table view, a set of confusion matrices, a model interpreter view, a rule panel showing a list of rules that creates various objectives, and the objective function view that visually represents an objective function. The table view shows the training and the test data on the left. The parallel coordinate view on the right allows users to sort, search, and filter the data. Users can construct machine learning models to see confusion matrices of the training and the test set. The red cross icons show the incorrectly predicted labels of the target variable. The model interpreter view allows users to inspect multiple classifiers. Models are shown as a parallel coordinate or a star plot view, which allows where each axis is a specified objective. Clicking on a model's name on the top updates the table view with its predicted output. The objective function view lists the specified set of objectives and constraints. Users can specify objectives by interacting with the data in the table view or by clicking any of the shown objectives in this objective function view. These objectives can be added or dragged or removed on the fly, then weighted to specify the relative order of importance. We first investigated the design space of the set of objectives and constraints that can be interactively specified to a model solver to construct classifiers. Using an affinity diagramming approach, we studied over 60 research papers from the literature, based on which we categorized objectives into 4 categories: instance-based, feature-based, train objectives, and test objectives. I will discuss only a few of these next. To know about all of them, I recommend please read the paper. To understand these objectives, consider the employee salary dataset from the city of San Francisco. Every row in the data is a job type, such as attorney or nurse. The data contains over 22 attributes, such as salary, dental benefits, overtime, etc. Instance-based objectives are specifications that users can make based on the data items in the training set. The similarity constraint captures the degree of similarity or difference between data items. In this data, a user may specify a set of similar job types, say a manager or an administrator, and in doing so, the user may expect them to be predicted in the same class. Various systems in the past have sought similarity between data samples. For example, Thomas et al. In their paper discusses similarity metrics to infer if an object A is similar to B or C. In QUESTO, users can specify similarity through a drop-down selector and then directly selecting data items from the table view. The critical constraint lets users specify a set of data instances to show that correct prediction of these are critical for them. For example, in the salary dataset for a user, the correct prediction of a job type with medium retirement benefits from 2012 to 14 may be of more value than other data items. In the literature, a popular classification algorithm called LINE reports a model's performance based on a set of critical data instances. Feature-based objectives are specifications that users can make about the columns or the attributes of the data through the parallel coordinate view. They can specify features that are highly correlated or that are highly variant in relation to one another. The objective function will penalize or reward the model respectively if those features are used. And finally, users can specify a set of hand-chosen features. Models will be rewarded if these features are used. Next, I will walk you through a demo of QUESTO, emphasizing how users can interactively construct objective functions. Megan is a public policy analyst and loads the salary dataset with 10,000 job types as data samples with 5 class labels of department for each job types. They construct a classifier to check the base performance as a set of train and test confusion matrices on the right. She sees the red cross icons to notice that there are many samples that are incorrectly predicted. They specify a set of data samples with median retirement benefits from the year 2015 and 16 as critical by filtering them using the parallel coordinate plot on the right. They can record any constraint they specify as a rule to review later in their analysis process. They review the objective function to check the specified objective critical. They also review a set of classifiers to see how the models has been constructed. Next, they specify the constraint candidate on a set of data items of the label cultural because many data instances were incorrectly predicted in that class. They construct a new set of classifiers to see the updated objective function score. They see that the performance improved slightly on the training and the test set. Next, they look at the scatterplot metrics to find a set of job types with exceptionally high salary, which are outlier and noise in the data. They filter the table using the feature panel and then specify a set of data items as ignore constraint. Megan looks at the rule panel to see that every constraint that she has specified is recorded as a rule. Next, Megan constructs new classifiers to find that the model is grossly overfitted. It has 99% training accuracy while only 48% test accuracy. She specifies a set of test objectives to update the objective function and next constructs a new set of classifiers to review the performance of the models. Finally, happy with the model, she exports it for further analysis. We conducted a qualitative and quantitative evaluation of QUESTO to validate its effectiveness. Apart from using a visual interface such as QUESTO, there are two other methods to create classifiers. One is by writing code in Python or R and running them via command line interfaces, which we also refer to as CMD interfaces, or directly using AutoML platforms such as AutoMecha or OrangeML. We experimented with 16 participants with some background in machine learning. We compared QUESTO with CMD and standalone AutoML. Our dependent variables were task completion times, model accuracy, and constraint satisfaction score. For the quantitative evaluation, we asked participants to specify a set of pre-specified constraints on the salary dataset containing 5,000 data items. For the qualitative evaluation, we asked participants to freely explore QUESTO and construct objective functions on the IMDb movies data containing 5,000 movies, with a goal to improve the classifier's performance. We studied qualitative feedback from a post-study open-ended questionnaire in addition to the video and audio recordings of the participant screen. We observed that participants found QUESTO allowed them specification of meaningful constraints via objective functions. One participant said, I think the constraints make a lot of sense to me. When I test models, I frequently look at specific data items to verify if the classifier modeled the data correctly. They also seem to find model interpreter view intuitive to inspect models in relation to how well the model addressed the specified constraints. However, on the con side, we observed that participants specified conflicting constraints. For example, at times they specified the same data samples as examples to ignore and similarity constraint. This caused confusion to the model solver in selecting the right model for the user. A few advanced participants expressed that they were uncertain about the underlying modeling process as it was not transparent enough for them to adjust the models further. Quantitatively, we found QUESTO is easier and faster than CMD based on Likert ratings and log data of task completion times. For various subjective aspects such as intuitiveness and learnability, participants slightly preferred QUESTO than CMD. Further, we also found that QUESTO addressed subjective user constraints in the objective function better than standalone AutoML, though it produced marginally less accurate models than standalone AutoML. QUESTO employs a feedback loop between the user and the system to communicate intents and to inspect models. Further, we observed that in a multi-objective optimization problem, satisfying every objective might not be feasible. Thus, formalizing user goals as an objective function facilitates understanding various trade-offs in model selection. Thanks for listening. With that, I end my talk. I'm currently on the job market, so please feel free to contact me at my email.